Okay, these problems are seem to be deceptively simple because there's really only two things you got to remember. And that is that Archimedes Principle always applies, whether it's floating at the top or sunk at the bottom. The buoyant force will always, always, always be equal to the weight of the fluid displaced. Displaced means pushed out of the way by the object. Now, if the object is also floating, you get a twofer. You get one more piece of information. Not only is the buoyant force equal to the weight of the fluid displaced, it also has to equal the weight of the object. And that means the 10-ton boat, to float, has to displace or push out of the way 10 tons of fluid. As easy as that seems, we've seen that it can be challenging. At the end of class, I gave you this problem where you're floating in your boat. You've got bricks of gold. You mark the level of the water on the side of the pool, and then you throw the gold bricks to the bottom of the pool. And the question is, what happens to the level of the water in the pool? Does it go up, stay the same, or go down? You all know the right answer. I told you at the end of class. Make me proud. Everyone get it right. Okay. The answer is indeed it goes down. But why? Some of you are just remembering from last day, I'm afraid. Let's talk about it. There's the water in your pool. I'm thinking you should use more chlorine. And when you've got that brick of gold in your boat, the boat rides very low in the water. When that brick is floating, it displaces an amount of liquid, water, equal to its weight or its volume. Its weight. When something floats, it displaces an amount equal to its own weight. And the question is, how much water does it take to equal the weight of a brick of gold? A lot. A lot. So it is displacing a lot of water by making that boat ride very low in the water. If, on the other hand, I throw that brick to the bottom, now it displaces an amount of water equal to its own volume. Where that brick of gold is now, water used to be. Had to go elsewhere. And so you see that it's not displacing nearly as much water with the brick at the bottom of the pool, so the water level in the pool goes down. Now it does that because the boat is now riding very high on the water. Okay? Check that your neighbor follows that reasoning and could answer a question like that on the exam. Now, the next question is a review of an example in the textbook, and this example goes something like this. You agree to meet a friend at a restaurant in the middle of the day, and your friend's not there when you get there, so you get seated. The waiter brings you a glass of ice water. A single ice cube is in that glass, and the water level is right up to the brim. You wait and you wait and you wait in the heat of the day. Your friend never actually shows up. You got stood up, sorry. But during the course of waiting, that ice cube melts. Does the water spill over the top of the glass? Does the water level go down, or does the water level stay the same? Talk to Nimrod. Tell Nimrod what's going to happen. Okay. Now, let me address this problem a little bit differently than it's done in the book. Suppose I start with a very large bucket and I fill that bucket with water right up to the brim. And then I take a large chunk of ice. How large? This chunk weighs 5 pounds. It's a chunk. And I take that chunk of ice and I lower it gently into the water until it floats. Now that's going to spill some water onto the table. How much? How much water is going to spill out? 5 pounds, yeah. And I can prove that with a free body diagram. The weight, it's 5 pounds. That's why we call it a 5-pound block of ice. And the only other force is the buoyant force. There's no acceleration, so it has to balance the weight. And that is the weight of the water that's been displaced. If you started with the bucket full at the top, displaced means spilled. So that means I've got 5 pounds of water sitting on the table. I lift up that block of ice, and now I've got room in that bucket for some more water. How much water? 5 pounds. And if I take that 5 pounds of ice and I hold it in the sun above the bucket, I'm going to melt it into 5 pounds of water. Drip, 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 5 pounds of water, and it'll be right up to the surface. So the answer is, as that ice cube melts, the water level stays right at the brim. Now some of you are thinking, Greg, how can that be? Because the ice was up and over. Okay? It was up and over. It didn't fit. But that's the whole point. Ice has a smaller density. It takes up more space than water does. 5 pounds of water takes up less space than 5 pounds of ice. That's why the ice was sticking up out of the top. Okay? When the ice melts, it gets smaller. It fits into that part that was the ice cube below the surface. Now that's a very different problem than if I took the ice cube and I super glued it to the bottom of the glass and then filled up the glass to the brim and waited for the ice to melt. In that problem, the water level would go down. As the ice melts, it would take up less space and the water level would go down. Okay? But that's a different problem than the one we were trying to solve. See if your neighbor's on the bus, please. Let's look at the problem that you voted off the island. You have 3 buckets, each filled with the brim, one with liquid X, one with liquid Y, and one with liquid Z. We find that if we take a ball of clay, and we know that the volume of that ball of clay is 5 centimeters cubed. We know that if we put it gently into each of these buckets in turn, we get liquid that spills out. And when we put it in bucket X, we get 5 centimeters cubed spilled onto the table, and it has a mass of 4 grams. On bucket Y, we have 5 centimeters cubed, and it has 3 grams, the spilled liquid. And for Z, we only have 3 centimeters cubed, and it has a mass of 6 grams. So this would be 4 grams, 3 grams, 6 grams, 5 centimeters cubed, 5 centimeters cubed, 3 centimeters cubed. And the first question we're asked is, in which of these buckets did the ball of clay sink? Well, which one? X and 1. Yeah, it sank here. It sank here and it floated there. And that's because when I put the ball at the bottom, where the ball is, liquid X used to be. It had to go elsewhere. And so I displace an amount of liquid equal to its own volume. Likewise here. But here, only 3 centimeters cubed spilled out. So that tells me that this thing must be floating. And it's floating with 3 centimeters cubed below the surface and 2 centimeters cubed above the surface. Now, here's the big idea. If you want to know the size of something, the volume, the number of cubic centimeters that it takes up, look at an experiment where it sinks. But those experiments will tell you nothing about the mass. If you want to know about the mass, you look at an experiment where it floats. Think about this experiment here. This experiment here doesn't tell me whether this is a ball of clay that's this big, or whether it's a piece of the center of a neutron star, you know, with the mass of this whole planet, and don't take it home to mom, okay? I learned nothing about the mass when it's sitting on the bottom, only about its volume, okay? So in this problem, we're asked to find the mass. Now, when something floats, there's only 2 forces. There's the weight force, which is the mass of the object, times g, and there's the buoyant force, and that's equal to the mass of the displaced liquid, times g. And those are equal. And if the weights are equal, the masses are equal, and so that means the mass of this ball of clay must be 6 grams. And that means that the density of the clay is equal to the mass of the ball divided by the volume of the ball. That's going to be 6 grams over 5 centimeters cubed, or 1.2 grams per centimeter cubed. Now there's another way to solve that. Remember, I told you, when you only see 10% of the iceberg, you don't see 90%. And it's the part you don't see, the part that's submerged, that tells you what fraction of the liquid's density the floating object's density is. Now the density of liquid Z is 6 grams per 3 centimeters cubed, or 2 grams per centimeter cubed. If I look at that ball floating in liquid Z, I see that 60% of it is submerged. And so that tells me that the density of clay is going to be 60% of the density of Z. Now every time you see a percent, divide by 100. That's 0.6. And anytime you see the word of, that means multiply. And the density of Z, we just said, is 2 grams per centimeter cubed, and that's 0.6 times 2 is 1.2 grams per centimeter cubed. So I can work that 2 different ways. Now the next question asks, in which of those buckets did the clay experience the smallest buoyant force? Now the buoyant force is always given by the weight of the fluid displaced. I've got a table here that tells me the grams displaced. The weight is just the mass times g, so whichever one has the fewest grams displaced will have the smallest buoyant force. So it's smallest in liquid water. Check that your neighbor's on the bus with that problem and ask them why they voted it off the island. Now, I would like to caution you, at the end of the chapter there's a formula that says that the buoyant force is equal to rho GV. And that formula, I really, really wish it were not there in the chapter. Well, Greg, it's your chapter, it's your book. Why is it there? It wasn't there when I wrote it. It was added later. The reason I don't like it there is because you memorized G as 9.8, call it 10, newtons for every kilogram. Well, this formula is only going to give you a correct answer if you put your density in kilograms per meter cubed and your volume in meters cubed. And that's not what we typically do. We use grams and centimeters cubed. And so you end up getting answers with this formula that are 1,000 times too big. Let me show you how I would like you to solve these problems, finding the buoyant force. I'll leave that there. Let's look at the problem you just turned in. If this is water, and you take a rock, and you put it under the surface of the water, and let go. What is the acceleration of that rock right after you let go? Well, we're told that this rock has a mass of 400 grams and a volume of 100 centimeters cubed. That means it has a density of 4 grams per centimeter cubed. That's a much higher density than that of water. It's going to sink like a rock, so to speak. Now, if I want to find the acceleration, I draw a free body diagram. I have a weight force. Well, that's just m times g. But if I take 400 grams and multiply by 10 newtons for each kilogram, I'm going to get 4,000. Boy, that's a lot of newtons. And that's silly. Because I can't cancel grams with kilograms. So what I have to do is I have to convert that mass to kilograms. That's 0.4 kilograms times 10 newtons for each kilogram, or 4 newtons. And now I need to find the buoyant force up. Well, the buoyant force is equal to the weight of the fluid displaced. Where that rock is, water used to be. It got displaced. So I imagine a ball of water exactly the same size as the rock. And I ask myself, what would that ball of water weigh? If I put that ball of water on a scale that read in newtons, how many newtons would it weigh? Well, let's figure it out. This is water, and I know the size of the ball is 100 centimeters cubed. But if I want to know its weight, I got to find its mass. How many grams of water would that be? That's the nice thing about water. It's 1 for 1. The density of water is 1 gram for each centimeter cubed. So if I've got 100 centimeters cubed, I've got 100 grams of water. Well, that's 0.1 kilogram. And that's going to weigh, if I put a weight force there, that would be 0.1 kilogram times 10 newtons for each kilogram, 1 newton. And that's going to be the buoyant force on this ball of water. And I know that because Archimedes taught me. That water's not going to go up or down. Its buoyant force has to equal its weight. But because this has the same size as the rock, I get the same buoyant force. And so now this rock has a weight force down of 4 newtons, a buoyant force up of 1 newton. That gives me a net force down of 3 newtons. So if I go F net equals MA, this is 3 newtons down, equals 0.4 kilograms times A, and I get my acceleration. See if your neighbor got that right. If not, do what you gotta do. Okay, let's move on. We're going to move on to a primordial pond. And at this pond, we have a pressure at the top of 1 atmosphere. We know if we go down a distance of 10.3 meters into fresh water, we double that from 1 atmosphere to 2 atmospheres. Now, this pond has a nice underwater cave. Kind of fun. And my question is, what would the pressure here be? Would it be 2 atmospheres, greater than 2, or less than 2? Now, another way of asking this question is, if I were to drill a horizontal hole through the rock with a long drill bit, after the hole filled up with water, would water stream to the right through the hole, or stream to the left through the hole, or just be stagnant in the hole? What do you think? Oh, I think it's Friday. Yeah. It wouldn't go anywhere. I would have the same pressure here as there, and that is one of the most powerful parts of our formula. This was our formula, remember, that the pressure at 2 is equal to the pressure at 1 plus rho GH. Never at any time did we care what shape this container of liquid was. It doesn't matter. All that matters is how much deeper point 2 is than point 1. Okay? Now suppose, this is just kind of off topic here, but suppose that there was a villain, an evil villain, and he had his lair down here. Okay, and so this is all water. And this is air, and he's got a little dock here. He's got henchmen that are ugly. He's probably got a submarine. They usually have submarines. And the question is, if that's 2 atmospheres, what's the pressure of his air in his evil headquarters? It's got to be 2 atmospheres. It's got to be pressurized. And if that supervillain says, you know, it's starting to stink in here. It really is. All you bad guys are just not taking showers. It stinks in here. And so he drills a vent to get some fresh air. What do? Yeah, we just flush out all the bad guys. Nice technique. Okay. So, I got to tell you. Yes, sir.
That little corner there in the cave, what if it was just like a pocket of, like you brought the little thing down?
What if it were down here so it was just a little hole?
I don't know, like it was completely covered. And it was like
if it went all the way down?
Yeah, it was like a pocket of water down there.
Oh, in that case,
would it go back to
it really depends on how you put the water in there, at what pressure you put it in. At that point, I can make the pressure anything I want up here, and then from there I'd use the formula. But if
you did it suddenly, would it be then too?
If I just went straight down, all of a sudden this just grew down, then this would be still 2 atmospheres, and whatever, you know, if I went 10.3 meters below, it would be 3 atmospheres. Have any of you been to Cancun, to the cenotes? Any of you? Okay, down in the Cancun area of Mexico, they have an underground river that just kind of runs under everything. And every now and again, the ground just falls in, it just caves in. And you've got a sinkhole. And if you go down in that sinkhole, there's just beautiful crystal clear water. And if you look under the edges, there's all these stalactites. And if you look down below, there's stalagmites. You're in an underwater cave. And what my family would love to do when our kids were in high school is we'd go down with flashlights. And you'd dive down and you look up for air pockets. And then you'd go for the air pocket and you're in a little new cave. And then you'd go down and look for a new air pocket and you're in a new cave. As long as you remember where you came from. One year, we were there. My oldest had just gotten married the year before and brought his wife. And we went to a new cenote that had just been discovered. The farmer just found it on his land. and someone told us about it. We went out there. Gorgeous cenote. And we spent time there, and after a while, we noticed that it had been 45 minutes since my oldest two boys had been seen. They were gone. We searched and we searched and we searched. We couldn't find them. My son's wife was just getting frantic. She was panicked. And then, after an hour and a half, my two boys came walking through the jungle. What had happened is one of the boys had looked down, seen some light, and went through a tunnel to get to it. It was a long tunnel, just barely had enough breath to get to it. His brother, not wanting to lose his brother, went after him. They got in there and they thought, this is a way cool cave. But when they went down to go back, there were all sorts of different holes going every which direction. And they kept going down these holes and they couldn't find out. And so they just didn't know what to do. And finally, they climbed up the walls of this cave and dug themselves out like zombies out of the top and came marching back through the jungle. So we almost lost them. Okay. It turns out on this particular day an asteroid lands, and because of that crash, it sends a shockwave. The monkey is dead. Okay? It's a big enough shockwave to send the pressure at the top from 1 atmosphere to 5 atmospheres. Now the question is, what happens here? Does that go to 4 atmospheres or does that go to 6 atmospheres? What is that?
6.
Okay. And I should have said 6 or 10. I'm sorry. It goes to 6. And that's because I'm adding 4 atmospheres to the right-hand side of this equation. The density of the water doesn't change. You're on the same planet. The depth stays the same. Whatever I do to the right-hand side of the equal sign, I got to do to the left-hand side. And so this has to go from 5 to 6. Now, I don't have to use an asteroid, okay? Waiting around for an asteroid is kind of boring. If I just get me a giant and a plunger, if my giant is big enough, there's no limit to how hard he can push on that plunger. And I can make whatever pressure I want at the top of that surface. That pressure at the top of the surface is going to be transmitted throughout the liquid. The first person to actually verbalize this was a scientist by the name of Severus Snape. No, but he does look a little bit like Severus, doesn't he? This is Blaise Pascal, a mathematician, and he said any change in pressure applied to an enclosed fluid is transmitted undiminished to all parts of the fluid and the enclosing walls. This is the very foundational principle of hydrodynamics, of hydraulics. In other words, this is how all of those great big huge pieces of equipment on the farm work. Okay? Now, we're going to explore this idea with a new Olympic event called dueling syringes. And I need some, are you two willing to volunteer for this? Come on up. Okay. Okay, Elizabeth, would you stand facing, what's your name?
Bennett.
Bennett, okay. And this is the way we're going to play this. I've got 2 syringes that are connected with a tube filled with water. Each of these syringes are partially filled with water. When I push on one plunger, it pushes the other plunger out. Okay? And so what I'm going to do is I'm going to hand each of these individuals a plunger. They can each use a single thumb. When I say go, their goal is to push theirs all the way in so that the other one goes out. Okay? Are you willing to play this? Okay. Are you ready? Okay, only one thumb, and wait until I say go. Ready, set, go. Whoa, Bennett, you won. Oh, dude. Now you've come to expect that these things are rigged. If I turn this around and give Elizabeth the large plunger, 1, 2, 3, go, yeah, she loses this time, okay? Whoever's got the large, let's give them a hand, folks. You could have done better than that. Whoever has the large plunger is going to lose, okay? And that's because if they create the same pressure right next to their plunger, it's going to be a tie. No water's going to go to the left, no water's going to go to the right. But that's if the pressure's the same. But the pressure is the force divided by the area. So that means whoever's got the bigger area of the plunger has to provide a bigger force just to tie. If the ratio of the areas is 4 to 1, that means Bennett would have to push with his thumb 4 times harder just to tie. Now this is how we make hydraulic equipment work. Let's say I want to lift a car and it's going to take a force of 1,000 pounds. Well, I can't push with 1,000 pounds, but I can push with 100 pounds on a good day. So what I do is I set up a reservoir. I wouldn't fill this with water because that's going to rust everything, but maybe some kind of oil. And this reservoir would have a cross-sectional area that's 10 times that of this one, okay? And that means, since the pressure at the surface is going to be the same depth, that means if I look at the force, if this one has 10 times the area, I'm going to get 10 times the force. Now think about that. If I push with 100 pounds down, that plunger there pushes up with 1,000 pounds. I push with 100 pounds, I get 1,000 pounds. That sounds like free lunch. Whenever I get something for nothing, I get a little nervous. What's the catch here? Why is this not free lunch? Yes, sir?
Is it because it also puts that pressure on all the sides?
It does put it on all the sides, but it does give me 10 times the force pushing up. Where's the catch?
You have to push farther than the car moves.
Yes, if this plunger here goes up 1 inch, well, I got to fill all that area underneath it with liquid, whatever oil you got in here. That means I got to push my plunger down 10 inches. So that means my force times my distance is equal to my force times my distance. Force times distance. That sounds familiar. What's that? Verk. The Verk in is equal to the Verk out. My 100 pounds times 10 inches is going to give me 1,000 pounds times 1 inch. I don't get something for nothing. I trade force for distance. Okay? If I want a bigger force, I've got to push a bigger distance. But that's worth it to me because I need that force. Now in practice, you would actually put point B lower in the liquid so that you already start out with a higher pressure there to support the weight of the actual device. Okay? Now on the exam, the final exam, any question about Pascal's principle would be a qualitative one, an easy one, just checking to see if you understand the basic idea. It wouldn't be a huge calculation. Let's look at one more idea. We go down to a highway that suddenly goes from 4 lanes to 1 lane. That's frustrating. And we're doing a research project, so we plant Stick Picard and Stick Spock at these 2 locations, and we give them each one of those counters that the greeter at Walmart has. And Stick Picard and Stick Spock count each car that goes past them. They do that from morning till night, till midnight. How do the 2 numbers on their 2 counters compare? Who's got the bigger number? They got to have the same number or else some of those cars were being beamed up to the Enterprise, right? Yeah, they got to, whatever went past Picard has to go past Spock. What is different is the speed. Over here, where they're all waiting for their turn, they're barely moving, they're honking, but they're barely moving. And then when they finally get to the place where they can start going, they go zoom, right past Spock, okay? You've all been in this traffic jam before. Now, we're not interested in highway dynamics or the motion of cars. We're talking about fluids, okay? So let's replace this highway with a pipe. And that pipe goes from a fat pipe to a skinny pipe. And we're going to look at a liquid going through that pipe. And it's going to be a chunky liquid. Now, those of you from New Jersey know what I'm talking about, okay? And I choose a chunky liquid because I want to concentrate on that chunk there. That chunk right there was going slow, waiting its turn. It's about to go really fast, past Spock. That means that chunk is being accelerated to the right. Now, the only way I can accelerate that chunk to the right is if it has a high pressure behind it and a low pressure in front of it. Now, look at the trade-off here. Where the speed is small, the pressure is large. Where the speed is great, the pressure is small. This is what keeps airplanes in the air. And it's called Bernoulli's Equation. Daniel Bernoulli, also a mathematician, gave us this equation that relates the pressure at any point in a fluid to the speed in that same fluid. Now, this is a simplified version of his equation, assuming that everything happens on the same level. If one part of the liquid is at a higher level, we need another term in here. But this is going to be all that we need here. What that means is that whenever I've got a high pressure, I have a low speed, and vice versa. Now, we've seen this in this class before. We just didn't recognize it. On the second day of class, I showed you this little truck. And you remember, on the second day of class, that was just magic. And that was just my way of saying, this class is going to be magic. But what's happening here is that this little smokestack is actually blowing air. And so this little styrofoam ball sees a region right above the stack that has a velocity. A velocity means a low pressure. The rest of the air in the room is not moving. So that's a high pressure. So anytime this ball wants to get out of the stream, it's going from a low pressure region to a high pressure region. Now I can do that on a bigger scale. Danger, danger, Will Robinson. Let's see if I can spin it. Do it. Oh. Come on! You're not getting supper. I just broke it. This is going to come out of my paycheck. Okay. Now, if you think about an airplane wing, and think of the forces on that wing. Okay, so here's an airplane wing. Actually, that wouldn't be a very good airplane wing, would it? No, an airplane wing, you want to have an airfoil, like that. And if I think of that airfoil slicing through the air, let's look at two chunks of air. Well, this chunk of air, as the wing goes past it, it will end up here. And this chunk of air will end up here. And so relative to the wing, this chunk of air has a small speed, and this one has a big speed because it's traveled a further distance in the same amount of time. That means I would have a low pressure here and a big pressure there, giving a net push up that keeps the airplane afloat. Now, here's another thing that you can do if you don't have an airplane. If you go home and get a spoon and go into your kitchen and get the faucet running so that you've got a stream of water. And then take that spoon and just hold it. Those are your fingers. You got skinny fingers. Hold that spoon near the water, but not touching the water. Just close to it. And that spoon will get sucked right in. Because that flow of the water is a low pressure area. And so the air around is going to push it in. Now, if I take this blower and don't want to lose that. If I now, what I'm going to do, Barrett didn't agree to this, but he's a good sport. I'm going to cock this, move your hand, be a man about it. What's happening is that the air, in order to escape from around the ball, has to be going very, very fast between this surface and the ball. That makes that region between the surface and the ball a low pressure area, and it actually sucks it in at the same time it's blowing air around it. Now I've got one last demo. If I take this blower and I hook it to this contraption here, where I've got a fat pipe, a skinny pipe, a fat pipe. Think of Stick Spock and Stick Picard. Where's the pressure going to be high? Where is it going to be low? I'm going to blow from those regions air up these stacks, and I'm going to float these ping pong balls. Predict with your neighbor where the ping pong ball is going to ride high and where it's going to ride low. Okay. This is a high pressure region, a low pressure region, another high pressure region. And again, using this principle, Bernoulli's equation, let's see if I can land them. Okay, folks, have a good weekend.